in my case, the daddy face. And that is, you see your kids doing things that are kind of, I don't know, pathetic. And you had to go, good job. Way to go. Right? Like, for instance, when you try to teach a kid to swing. This is me. This is me doing my impression of my children learning to swing. They really want to swing. So first, all right, and you did this. I know you all did this. First you were just like, Daddy, do a super underdoggy.
Yes.
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 Did you not love super underdoggies? I know. And you push the kid, and you get underneath there, and then, yay, another one. Okay, yay, another one. It's like, Daddy worked all day. Good, super underdog. Daddy worked all day. Can't you just swing for yourself? Like, no, super underdog. So she just wants so much for them to grow up and start swinging for themselves. So, Jake, don't you want her to be a big boy and swing for stuff? Yeah, okay. And you show them, you model for them. Here's what you do, right? And they get on there and they go like, you know that's what you did, didn't you? And I'll be darned if the swing, yeah, you did so. Lizzie, don't you did. You don't remember it. This was you. This was you. And everyone in the park is like, there goes another pathetic kid who doesn't understand the concept of resonance. And here's what I said to my son. I said, Jake, you are never going to increase the amplitude of that swing unless you learn to add energy in phase with its natural frequency. It won't resonate otherwise. And he just cried, Mommy, he did it again. Yes.
But to this day, you still want somebody to push you on the swing, though, right?
Not me. I'm a big boy.
Nah, dude.
I'm a big boy.
I like getting up to speed.
You know what's awesome, too? When you're little, you're so unbreakable. And you can just jump off swings.
Oh, except if you're a second grade.
I do that all the time.
Because my friend jumped off the swing and shattered her elbow.
Oh, that's not good. And that's why.
Why do you have to be in second grade?
William, listen. Sadly, that is why they no longer have swings at our schools.
That's stupid.
I know it is. I'm like, are you kidding? I couldn't believe it. No slides, no swings.
There's slides in my elementary.
At Brownsville
Where?
Elementary?
At Silverdale.
Not anymore.
Yeah, they have their...
Oh, yeah, they had that big...
The baby swing. They used to have the one that went down the hill.
At Brownsville?
You guys must have been like the last year they had them then.
Mr. Sampson, at Brownsville Elementary, I was like in second.
Hey guys, whoa! Bring it down. Let's have one conversation. I'll get you next, gentlemen. Go ahead.
Alright, well, I think I was like in second grade, but Brownsville Elementary, they had like this huge metal sign.
Yeah.
Well, apparently some kid tried skateboarding down it.
Isn't at our school?
This could be an urban legend because. What school was that?
Emerald Heights.
Okay, we had that legend at Cougar Valley. I bet you it never happened. I bet you just somebody said, someday someone's going to sue us. Let's just get rid of the slides.
No!
So,
How dare
come
they?
on,
The best part of my research, I got sent to the principal's office once.
They probably don't even play tetherball anymore or Foursquare.
Oh,
If you play Foursquare, what if you hurt your elbow? Anyway, now watch. Yes, Angelica, sorry. Excuse me, Taylor, you go ahead.
We had like 2 playgrounds. We got one for the
Excuse me.
first through like preschoolers, and we had like one for the second through.
Oh, the big kids slide.
The big kids.
You had to graduate.
We had one slide. It was like a tube slide, so no one could get hurt. And kids were always trying to climb up it, and they had to. I had 7th to 7th grade. So if you got caught trying to climb up the slide, like you got a timeout. Like
who actually?
I had.
All right. Well, here you go. Kyla, excuse me. Sorry to get you guys all riled up. So this is going to be my model of a slide. A slide is basically a pendulum. Okay? And now what happens is this. If you just try to get this thing swing, really the goal is to get a high amplitude swing. Now, there's a certain frequency, and if I remember yesterday, frequency is related to wavelength and velocity. The frequency of a wave is equal to the velocity of the wave divided by its wavelength. And that basically locks it into a certain frequency because it has a certain wavelength and gravity's going to make it accelerate at a certain rate. Now, what happens is, if I think about what this frequency is, it's like 1, 2, 3, 4. If I add energy at that frequency, 1, 2, 3, 4. What happened to the amplitude of the swings?
Increase.
We call this resonance. Resonance is an increase in the amplitude of an oscillation when energy is added in time with what we call its natural frequency. This is the frequency, and the only frequency that this pendulum is going to operate at. Short of going to a planet with different gravity, a pendulum of this length is always going to have this frequency. And if you add energy to it that is not in phase with that, it's going to cancel out. So watch this. I'm going to try to, this is a kid trying to get to really go. I really want this thing to swing. Daddy, it's not working. Just give me a super underdoggy. Kid, look, you can't just go fast. It's not a question. It's not a question of effort. It's a question of timing. It's all about the timing. It's skillage, right? You just gotta say, look, you gotta perceive what its natural frequency is, and just time yourself with its natural frequency, and it will resonate. And there's so many great examples of resonance that we can share with. But the first thing you got to understand is this: most objects have a natural frequency at which they oscillate. Well, like you don't have one. You're too complex and squishy. Right? But other things do. Things that are uniform in density. Like for instance, like here's a great example. I asked my wife if I could borrow some of her the crystal that her mom gave her or grandmother gave her, and she's like, no. I'm like, well, come on, honey. That's what you'll break. I'm like, but maybe say if you notice this, if you take like a wine glass and you get your finger wet and you go like this, and it goes like. It's all about the timing. What's happening is you're getting your finger to vibrate at the same natural frequency as that wine glass has a natural frequency it wants to vibrate at. And if you add energy and time with it, it'll resonate. So I don't have a wine glass, but I have this.
Yeah, there's like that.
Remember this? Oh, yeah. Now we can explain why it worked. We saw this at the beginning, and now we'll explain why. Okay. The idea is when I hold this here, it basically is going to bend. Essentially, it starts off like this. And then it's going to bend this way, and it's going to bend this way. So the ends are oscillating like this. But, it's a pretty rigid thing with a pretty strong elastic force operator on it, so it oscillates very quickly. And in fact, if I want to know what its natural frequency of vibration is, all I do is this. You hear that high-pitched sound?
I do that with forks.
The high-pitched sound what we have tuning forks, but that is the natural frequency that this wants to oscillate at. Now, if we were to hold this to what's called an oscilloscope, what we'd see is this is a frequency pretty close to 2,000 hertz. It's going like this 2,000 times a second. It's completing an oscillation. It's completing 2,000 oscillations every second. So if I want to make it resonate, if I want to increase its amplitude, at what rate do I need to add energy?
2,000.
2,000 times a second. Darn. Didn't quite make it to 2,000. Let me try again. Darn. Still didn't work. But there is another way. With my pixie dust that I got from Tinkerbell.
Is that what they call it these days?
You don't like it? Then I'm going to have you learn to do it.
And then tough.
I
don't like it either.
So the trick is, this is giving me a lot of friction. And the trick, so if, Kylan, I'm going to have you learn to do it. And here's the thing. Think like the kid on the swing. It's not about being fast. It's about being in time with its natural frequency. Okay? So the trick is, it's all about getting the right pressure. As you move your hand, you change the pressure on your fingers. And when you've got the right pressure, they'll vibrate up and down on it 2,000 times a second. If you put too much pressure, they'll vibrate, I think it's like not too many times, and not enough pressure, not enough times. I find it helps to line your elbow up with it this way, squeeze very tightly, grab very firmly here, and what happened to the amplitude of the sound wave?
It increased.
Why did it increase?
Because of the resonance.
What does that mean?
That means
Science.
it's the frequency of how fast.
Wiggle.
Yeah, I don't.
Wiggle.
I was adding energy.
My turn. brain is shaking.
I was adding energy
She gave me another.
in phase or out of phase with its natural frequency.
In phase.
And if you add energy in phase with its natural frequency, just like I did with the pendulum, like it's like, it will resonate. And when it resonates, what aspect of the wave changes?
How big is it?
The amplitude.
And what's the word for how big it is?
Amplitude.
Amplitude. Now, since I don't have video permission, you're not going to be on video, but you're going to do it. Here you go. Come on, you can do this.
I want to do it.
Believe in you,
Can
Kai.
I
Put this
can
at
I
the
do
middle
it?
part
Put
there,
them in the
okay?
video.
Now, wait, you need some pigs. First, go like this to make sure it balances. You got to be the center mass. Okay, now wrap your thumb around it, and then use your hand to hold the thumb down. There you go. Now get some. Oh, just a pinch. Wait, I just thought it was so gross. When I was a kid, I grew up in North Carolina. They used to advertise chewing tobacco on TV. It was Red Man, just a pinch between your cheek and gum. All right, all the kids at my school. All right, go ahead. Tight, real, grab hard, pull. Now go. Keep going. No, not fast. Hard. No, harder. And keep going. Keep going. You got it. More. I think the problem is your way you're clapping your hand here. Cameras, you got to only hold it in the middle, okay? So see, you're
Can I try it? I want to
No, concentrate. No, turn your hand. This
Shut
way.
up,
Makes me
Micah.
want to try it, will you?
Micah, middle name Appleton. Have fun drinking what's not it.
There you go. Okay. Now, try it one more time. You're gonna get it.
There
You're
are
not gonna-
4
you will hate
drops. I
it.
count.
You will hate it no more forever.
My turn.
Harder. Now keep it going. Hey! You've almost got it. That didn't quite count. Yeah. That counts. Give it up for Carla. Yeah. Oh yeah.
Can I do it?
Just to be rougher, I gotta get through the rest of it. Okay, sorry. Now, there's lots of awesome examples of resonance. And when I say awesome, I mean like super awesome examples of resonance. Well, let's start off with this. Residence.
Oh, dude, my dad has like a metal thing like that, and I like to go bang on one of the concrete and make it shake. It's really
Well, if you bang on the concrete, you chip it. And the thing about tuning forks is they have a very they're tuned. That's why they call them tuning forks to a very singular frequency of vibration. They only vibrate at one frequency.
It's not. It's a different one than
Most things vibrate at lots of different frequencies. Like say my vocal cords.
The metal part.
Excuse me, gentlemen.
No, it's just,
Most of them oscillate at multiple frequencies.
it's just the metal thing that I found in the shop.
As if we talk about later, that'd be great. So here's what's fun about these. Is that when you hit them. Now the reason that's so loud is it's on this box.
It sounds like a.
And this box has air in it.
Fairy.
And this air is resonating because basically this box is tuned so that the air vibrating in here completes an oscillation in the same amount of time as the tuning fork. So as the tuning fork goes like this, the air in here goes like this. They're in phase with each other. So what happens to the amplitude of the oscillation if you add energy in phase with the natural frequency? The amplitude gets louder, and we call that resonance. Yes, sir.
How come if you put your phone in a cup, it makes the sound louder? Or like in a bowl?
That might be more about, I don't really know the answer. It might be a directional feature. It keeps the energy from going out in all directions and focusing. I doubt if it's tuned. I don't think it's a resonance phenomenon. I think it's more of a directionality function. But now watch this. These are pretty cool tuning forks because I'm able to change the position of this one here. Right now, with these weights in this position here, they are tuned to have the exact same frequency as each other. In other words, this one likes to vibrate at the same frequency as this one. Therefore, the sound that this one makes should cause this one, if they have the same natural frequency, what should it cause this one to do?
Same thing, vibrate.
Okay, and the word I prefer is it causes it to resonate. So resonate means that your amplitude of oscillation increases because energy is added in time with your natural frequency. And since they both have, listen to the frequency of this one. Listen to the frequency of this one. That's the same frequency, right? So watch what happens. All right, this is cool. Hey, I'm not whacking that one. this one got this one to resonate. Believe it or not, this is basically essentially why the sky is blue. It's kind of weird, but air molecules resonate at the blue frequency. What do we got here?
Pictures from the dance?
Oh,
Why do they keep giving? What do you want to do?
They're frames.
You're just giving to me. How many do I have? What's that?
That's the only one.
What happened to the rest of you guys? No pictures from the dance?
I already got that.
Okay, I just thought I'd ask. Yeah.
It has a few.
Wait, I have a science question, not a dance picture question. So here we go. Go ahead.
What happens if you move the boxes like closer and more aligned?
Let's find out.
Is it the same?
It's about the same, okay? Now, but now watch this. This one here, I can change where this one is positioned. So I'm going to move this to a very different position. Now, this one should not be tuned to the same frequency as this one. I don't know if we'll be able to hear the difference in its frequency. It has a higher frequency now than this one does. Now what happens is, if I whack this one... Oh, you found another one?
Jeez, guys. Get on top of it.
Do your job.
Oh, yeah.
You're getting paid.
There you go.
No, we're not getting paid. Just volunteer hours.
Oh, okay.
All the noise. I love it when that happens with their who honkers and their tartinkers.
Oh, yeah.
All the noise. Okay. Hey, why didn't it work?
Because it's different. They're not tuned to the same frequency.
Okay, so our waves say they're not tuned to the same frequency, so they have different what we call natural frequencies. I like to get used to the idea a natural frequency. If an object has a natural frequency at which it wants to resonate, like say a tuning fork or a swing, then if you add energy and time with that, it will resonate. Now, how many of you are in band or play a musical instrument? So you've had to tune your instrument, right? Then you're probably familiar with what's called the beat phenomenon. The beat phenomenon happens when I make two sound waves that are almost but not quite the same frequency. And what happens then is the waves will get into phase with each other, and you get a large amplitude sound, so it gets louder. And then they'll get out of phase, and it'll go down. So what happens is, when you're getting close to having them at the same sound wave, it'll go like wah 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 wah. And we're tuning the same, okay? So watch. I'll do that with this one here. Right now, they should be way out of tune. It should be a very fast beat phenomenon. Right? Wah, 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 wah. We are way out of tune here, my friends. So let's change a little bit. I'll make it more out of tune. What'll happen to the frequency of the beat? It'll be even faster than that. Ooh, I can't make it vibrate that one. Not right at all. Okay. Now we'll get them close to. We'll get them close to, but not quite the same. Do you hear that?
Yeah.
Hey, that means we're getting really close. Tell me if I got it closer or farther away.
Farther away.
Oh, you cheaters.
Farther away.
Okay, sorry. How about now, Mr. Smart Guy?
It was be super close.
I'm not hearing any warbles, are you? We're tuned to the same. That means if we are tuned to the same, I should be able to whack one, it should make the other one resonate.
Yep.
Oh, we're in tune. Okay. Now, but wait, there's lots of examples of resonance I can show you.
Well, it's funny because it's like tuning forks.
Here is one of my faves. Jacob, I'm going to need you to take the camera around that way to go look at this rig I have in the back here. Okay? So just walking around this way.
I was outside.
All right. Right over there would be perfect. Yeah, right there is great. All right. So look what I have here. I have 4 washers I basically have 4 pendulums. 2 of them
Short.
have the exact same length and they're short, and two of them have the same length and they're long. So what I'm going to do is this. I'm going to take the long ones, and I'm going to pull this one back, and when I let it swing, what's going to happen is it's going to make this rope here bob up and down in time with the natural frequency of this one. And now what happens is, well, just watch this. It's pretty phenomenal. And here we
Oh,
go.
they're all starting to swing.
No, they're not all starting to swing. They might all start to swing, but only one of them is in phase with it. The one that has the same natural frequency begins to resonate. The amplitude of oscillation of this second one here.
What happens when you're swinging with your friend?
Does it? Does it?
Well, sometimes like the whole thing moves.
Only if the whole thing moves does that happen, because you got to be able to transfer energy from one to the other. Now watch what happens. If I've got these tuned just right, all the energy of this one pretty much will get transferred. The amplitude of this one will go almost to 0.
And that one will get higher.
Yeah, see, like this one is almost at 0 amplitude, and now what happens? It'll go back the other way. But notice how these ones don't start swinging. Why not? Right.
Because they're not the same length.
Well, obviously they're not the same length, but why does that keep them from resonating?
Because different frequencies.
Is your name Ryan?
He forgot his name. He's so excited. Yes, look at you, just riveted. Yeah, you made teaching easy. Okay, they have this. They have different natural frequencies. But let me ask you this. Okay,
Witchcraft.
witchcraft is a possibility. Caleb, who wasn't even here the last 2 days, but was here today. What do you think will happen when I let this one go?
The other one won't happen.
And my question to you is, sir, why?
Because they have the same natural frequency.
Look, they're definitely, and the other ones are not. Okay, so what happens is, if they have the same natural frequency, they will resonate. Otherwise, they don't.
Can that just go on forever?
What does your heart tell you?
No.
Which law of nature precludes that possibility? Ryan, you got it. You got it. Go. Harken back earlier in the year.
Earlier,
Way earlier in the year. Like our second unit of study.
I don't even know.
Oh, is it like when Gala said?
I'm confused. That's nothing to do with
There's a law of thermodynamics.
Oh,
Oh, the don't talk about it.
no, not that one.
He was making a Fight Club reference. Yeah, it's called the second law of thermodynamics. In any exchange of energy, some of it is always converted to heat. Hey, will you close that door for me so we don't hear my colleague again? Okay. All right, so let's walk this back up this way, if you don't mind. Now, when I was in graduate school studying geology, there was different places had different professors, and I remember we had this professor named Pradeep Talwani, who he was into seismology. It's cool. They had like this seismograph that was always going, so you could walk down the hall. Like there was a 6th floor, and you'd look, and you could always see like when there was earthquakes. Back then, they were still testing underground nuclear weapons, and he would label it like this. You could tell. And he taught us all, even if you weren't his student, how to look. And if it looked like this, if it looked like a Christmas tree, it was an earthquake. If it looked like a ball, it was a nuclear explosion. It was kind of cool. And some of my friends were his students. Okay. Now, but he had this one student. I forget the kid's name. He wasn't really one of my buddies.
Felipe?
No, but he. Excuse me, Colin. He was he was from Mexico City. And he was studying, seismology. He was working on his master's degree, and he was pretty. I mean, you may not know this, but if you get a master's degree, you pick a thesis usually, and that means like I'm going to research this one thing, and it's going to take me 2 or 3 years to complete this research, and I write a paper about it, and I have to defend it against all these other professors, and usually I get it published in some journal, and I get my master's degree. Right? Like my wife did it on these like little tiny planktonic fossils, and she used it to indicate that maybe dinosaurs didn't die off as quick as everybody thought, and she got to go to all these conferences and present. Well, here's this guy, and he was doing some kind of research. He was like 1.5 years into his research. This huge earthquake hits Mexico City. Man, he gets an airplane, heads back, because it was a big one, like a 8-point something, right? He flies back to Mexico City, and he's gone for like a long time. Like, man, what happened? I wish I remembered his name. He comes back, Kylan, and he's got this Kylan. And just zip, and he's got he's got this slideshow for us, and it was really mind-blowing because what he found was this, and he had to change what his thesis was going to be. Because here's what he found. Okay, so you have these buildings. Yep.
Oh, man.
So let's say this is Mexico City before the earthquake. All right, here we go.
Okay.
There you go. And what happened was, after the earthquake, this building was in rubble. And this building was in rubble. The other ones were damaged, but not in rubble. What do you think, Daniel? Oh, boy, we got some hands up here. Caleb wants to try.
Okay, so they're like a tuning fork, and they resonated with the ground frequency.
Perfect. So what happened was, each of these buildings, if you go like this to them, they're going to have a natural frequency that they wiggle at. The short ones, like a tuning fork, will wiggle faster. The tall ones will wiggle longer, and these ones wiggle somewhere in between. And the shaking was it had side-to-side shaking, which is not that normal in a lot of earthquakes, and it was prolonged. And what happened was it was tuned to the frequency of these buildings, and so he was able to link the seismograph information to information about these buildings and make suggestions about how you perhaps could prevent this from happening in the future. I don't know whatever happened with this research, but that was basically what it did. It was all about resonance. Yes, go ahead.
Isn't that what Tesla did with the earthquake machine?
Oh, the idea that you could add in energy to the earth. I've heard about this earthquake machine. I know the Mythbusters did something about it, but I've never really read about it.
It's awesome. They did it. They there was like this earthquake machine that they did,
and
it actually worked. It was
there was
like
an earthquake. We can make earthquakes now.
No, they just like it was like a
Yeah, we
small.
can.
They had a platform.
Yes,
And it
did that.
was
Well,
for, like,
the thing is that's not the same as the earthquake. It didn't cause movement along a fault.
it
Okay.
just
Well, yeah,
natural.
it's just resonance. So, like for instance, I've heard both, but this is true, and I've also heard this is not true. They say that I think it was the British Army would always break step, like they'd be marching, however they march, right? But when they got to a bridge, the order would be break step, walk however you want to walk. Why?
Because the frequency is the same.
Oh, yeah.
Have you ever been over a swinging bridge?
They've done that on the Mythbusters.
On a swinging bridge, you can definitely sense what and you can start on that swinging bridge. It gets going, right? But if you just kind of go across it like normally when you run, it'll start to go and then it'll go out. But if you add energy in time with it, it comes down. So if your bridge is tuned to the marching pace, the argument being is like the whole bridge. Right?
That's like
But that happened here in Washington, didn't it?
like Harry Potter.
We had a bridge fall down, and I'm going to show you a video at the end of the period where it happened. The Tacoma Narrows Bridge is one of the most famous disasters of all time.
Oh, I watched that. That was awesome. It was like
I know the dog.
I was like, no,
The dog that blew it.
But it was like, oh, yeah, and the bridge goes crazy.
why not save the dog?
Everybody.
I would save my dog. I would save.
Yes, ma'am.
Speaking about galloping Gertie, right?
That was what it was thinking. So they built this bridge, and shortly after building it, they're barely done with it, and they realized it was like 1941, I think, when they built it, and they realized, whoa! Every time the wind blows even a little bit, this bridge is like really gets going. And so they, before then you had to drive to Olympia to get to Seattle from here, and because it was, I'm not sure why it was built. If it had anything to do with the ramp up for the war, needing our naval base, getting people back to and from Bremerton, it might have been. But anyway, people often would not drive over it except for daredevils, because I don't know about you, I'm a little bit freaked out on a bridge. Can you imagine being on the bridge and it's going like this?
Oh, that would be so fun.
Maybe fun for you, not fun for me. I'd be like, I'll just drive to Olympia. There's a lot of people driving to Olympia. And then what happened was there was this, it wasn't like a storm, it was just like a windy morning. And what it turns out, looking at it later, what they realized is these uprights have a certain frequency that they would swing in the wind. So if you just like this does, if the wind is blowing on this, it's just going to start doing this. Well, it turns out the frequency with which the upright supports like to swing happen to be in tune with which the way that this like to wiggle side to side, and so it resonated. And when I show it to you, it's really remarkable because it resonated so much. It looked like it was made out of rubber until the whole thing fell down. They've since fixed it. But anyway, so those are examples of resonance. Now I need you to back that up a bit because I want to show a special kind of resonance that's important in music and in other things. But it's a special type of resonance called a standing wave.
Don't put me on the camera.
We shall now use my largest string.
Hey, can I hold the other end?
No, the other end is You see, a wall can do a better job than you. I agree.
Oh.
Yes, ma'am.
Wasn't also the other thing Freddy's like built like this? Like a snake?
No, it was not. It was built just like the one you see there today, except they altered it so that it couldn't resonate anymore. Please don't. Please stop. All right. So I have this, like many things, has a natural frequency at which it wants to resonate. So what I'll do is I'll just stand down here and add energy to it. Okay.
Hey, stop it.
Yeah. Jeez, Caleb.
Look, I'm not adding energy in time with its natural frequency. And so what's happening to the amplitude of the oscillations?
It's
Stopping.
staying small.
Just staying small, okay? But if I add energy in time with its natural frequency, let's see.
Now.
What happens to the amplitude of the oscillations?
It increases.
So it is resonating now. Now it's hard to perceive it this way, but allow me to explain what's going on here. When I do this, what happens is a trough goes this way. All right, and as the trough goes this way across here, it reaches this side here and it returns as a crest. And as it's returning as a crest is coming from the other direction. And when crest meets crest, what does it do? It gets large. Then they both hit the ends and they both return as troughs, and they meet in the middle as troughs. So what does it do?
Sound.
And but that only happens if I time it right. And so we have we find that this it can only resonate at certain frequencies. There is a lowest frequency, what we would call its natural frequency or base frequency. Let's just, for the sake of argument, say that this is 2 hertz, that this is 2 cycles a second. We call this the first harmonic. It was like jump rope.
Oh my
You
God.
should have seen the girls in North Carolina do jump rope when I was a kid. It was crazy. They'd get like 2 of them, they'd be like,
Double Dutch.
and they'd be like, whoa, they'd be doing all this stuff. I was like, what in the world? I can't even do this.
Well, I
I always
can.
tangle my feet and fall down and I'm embarrassed. I say, yes.
At my little private school, we had like this phase in 3rd and 4th grade where we only did double dutch. All the girls only did double dutch.
That means
every
2
set.
ropes.
Yeah.
Yes.
That's called double dutch.
That's called double
Because
dutch.
people in the Netherlands like to jump rope, I assume.
I don't know.
Okay.
But if you didn't know how to double dutch, like
You were a total loser.
You're a disgrace
Actually, I
to
knew
your
it.
family.
Loser.
I still know.
I'm a loser.
I still know how to double dutch.
I'm a loser.
All right. Just say, yeah, okay, here we go ahead.
There's this swing thing that you do.
It's so
It's a
exhausting
hydraulic
holding
kick, and you go like that, and they call it harmonics.
Okay, so look here. So the first harmonic looks like this. You have places where there's not much motion happening. We refer to these as nodes. So N-O-D-E. So this and this are known as nodes. A node is a point along what's called a standing wave, a wave that is self-sustaining, that remains at the equilibrium point. Now the opposite is you have points of maximum displacement. So halfway between 2 nodes, there will be what we call an antinode. I love the word antinode. Say it one time. It feels good.
Dance a note.
Antinode. Oh, look at your antinode. Now, so here's the deal. I'm going to expect you guys to be able to look at pictures of standing waves and analyze and say, hey, which harmonic is this? You can tell which harmonic it is by how many antinodes. There's one antinode. In other words, it's the part of it where you get. It's not where the crest and the trough are not 2 different antinodes. There is a point along here between 2 nodes where you get maximum displacement. That's called the antinode. This standing wave has 1 antinode. It is the first harmonic. But it's possible to get a second harmonic. And for the sake of argument, let's just say that this one was a 2 hertz wave. What do you think is probably true?
4.
Who said 4? Caleb, for which one?
Second.
Oh, but the second harmonic is going to be 4 hertz.
4.
But yes.
8.
A lot of people want to 8. They want to double each time, but that's not the way it works. You take the harmonic number and it's just a multiple of whatever the first harmonic is. So if the first harmonic is 2, and you're on the third harmonic, it's going to be 3 times the frequency. So watch, okay? I'm going to make a standing wave numero uno. Which harmonic is this?
Keep going.
Now, I'm going to make the second harmonic.
Keep
How
going.
many antinodes
You
will
can't
it
see
have?
him.
2. All right, here we go.
Keep
Here goes. So
going.
I can do it. I
There you
got
go. You can
skills.
see him.
I got
No,
skills.
go back. Stop.
Whoa.
Right there.
There it is. There it is. Wait.
Can I touch it?
No. Now look here.
I just want to touch it so bad.
This here is the node.
Solve it.
And I have an antinode there and an antinode here. Okay.
Whoa.
Let's try it again. Let's try again. So we can see where the node is, right?
Yeah, right there.
And I have 2 antinodes. So which harmonic is this?
Second.
And if the first one was 2 hertz, what would be the hertz of this wave?
4.
4 hertz. Now, if I can have a second harmonic, I can have a third harmonic. How many antinodes
6.
will it have?
Oh,
Antinodes.
3. No.
It should have 3
Yeah.
antinodes. Okay, so
Jeez, Mike.
So indecisive.
No.
Leave me alone.
you see the 3 antinodes?
Yeah.
12, 6, 9.
So
Ready
this,
for brain.
I'm now wiggling it 3 times more
It's
frequently
like staying
than I
still.
did for the first harmonic.
It's like staying
And if I can have 3 harmonics,
You can have 8.
4.
but let's not get crazy now. Let's go for 4.
If
It's
3
harder than
was
you
good,
think.
4 must be better.
Whoa!
Oh, who's got skills?
Let's go.
Let's
8.
go.
Eight.
Pay the bills.
8.
Let's just. I don't even know what I'm going to get this time. I'm just going to go crazy, okay?
All right.
But it's got to be a sustained wave. If it cancels out, then I'm out of phase. So it only resonates at the first harmonic, the second harmonic, the third, and the fourth, the fifth. So if I wiggle my hand and the frequency of my hand wiggles is not lined up with the frequency of one of those harmonics, I'll get destructive interference. The whole thing falls apart. Well, let's just see. But I'm pretty good because I've been doing this for 26 years.
Oh!
I lost it. I had it too.
Got it.
That's so hard to keep.
Oh, how many is that? How many? Count it. Count it.
That's
3,
it.
4, 5, 6, 7.
Are you not entertained?
I am entertained because that was
Me too.
freaking awesome.
Hey, don't swear, you're on.
Now, how is it that my voice sounds different from your voice? If both of us called up on the phone to talk to them, we're recording each other's voice, you can tell it apart. If you hear a celebrity's voice, you know it. And here's how. All right, what do you think? Go ahead.
Your vocal cords are longer.
Excuse me. Go ahead.
Your vocal cords are longer.
Well, it turns out you have several different resonating flaps of meat in your throat, okay? But here's what happens. Please listen. There's a Sorry, I didn't mean to gross you out with that.
Wait, what did you say?
I referred to vocal cords as flaps of meat. I guess that's a gross way of describing it. But here's the thing. Let's just say that this is a vocal cord, and this is my throat. Let's see.
Draw a head.
Look.
Is that a head?
Uh-huh.
No. Just a beautiful head.
It's a baby.
I'm singing. I'm singing. I'm singing.
I'm singing your song. I'm singing.
I love you.
What's that from? Oh, it's
Oh
from
my God, I
Elf.
love you. All right, so what happens is...
I love you. I love you.
I'm sorry if you haven't seen Elf, you need to see Elf. Okay, so the idea is like, when you go like, here's what happens. Let's just say the bass frequency for my vocal cord, let's just say the first harmonic for my vocal cord is, I'll make it easy, is 120 hertz. I can't make it go any lower than that, okay? And then the second harmonic would therefore be what? If my first harmonic is 120, what is my second harmonic?
212.
It'd be 240. But here's the thing. My vocal cord will be doing both. It will be resonating at both the first harmonic. That will be happening at the same time that this happens. They're happening simultaneously. Watch. Just watch. When I go like this, you notice you got different waves happening simultaneously on this. And so what happens is, my vocal cord is oscillating at both the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth.
The 10th.
Whoops.
That wasn't
and so on. And what'll happen is weird. And I'll show you next week if I can get the software to operate again, because every year they redo our computers. But what happens is this. Maybe in my vocal cords, the second harmonic and the fifth harmonic are where most of the energy is. There could be another person who has a similar set of vocal cords, but for them, their vocal cord puts most of the energy into the first, or the third, and the eighth. What happens is when you put these waves on top of each other, if you take, let's just say that the first harmonic has 120 hertz, it's a wave that looks like this. Okay, this is not showing the standard, I'm just showing a wave. And then the second wave has a frequency that's twice that. If you add, and the third harmonic is like is this. If you add these together, the wave that you get by adding all these together has this really complex waveform to it. And believe it or not, what your brain does is it categorizes people's voices by these complicated waveforms. So if I call you on the phone to tell you and say, I need to talk to your mom about the fact that you're not paying attention in class, Michaela. You'd be like, oh my goodness, that's Mr. Sampson's voice. I recognize that complex waveform because his vocal cords put most of their energy in the second, third, and eighth harmonic. And that's how we're able to make, and we call this the timbre of a voice. That's why no two violins have the same sound, because I think it has to do with how the different, sometimes we refer to harmonics as overtones in music, right? And basically what it means is that one violin string, for instance, it wiggles at multiple frequencies of its bass frequency. Same thing is true for a trumpet or any musical instrument you could think of. And the reason they all sound a little bit different is because they might all have the same set of harmonics. If I've got my violin tuned right, the first harmonic, let's say, is 120 hertz, so the second is 240, the next one is going to be 360, and so on. But it's where does this particular instrument put most of its energy? Where's the highest amplitude? That varies. So what I want to do now is this.